Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to go over another example of creating a buffer and calculating the pH of that buffer. So let's get into this. Okay, so this is example 2. So in this problem we're told a solution is prepared by mixing 100 milliliters of 0.50 molar ammonium chloride with 15.0 milliliters of 2.00 molar NaOH. What is the pH of the resulting solution? So right away we recognize that this is a two-step problem. The first step is going to be a complete reaction where the reaction goes to completion first, and then we do an equilibrium problem. The way we know that this is going to be a complete reaction first is because we're reacting a strong base with a conjugate or weak acid here. This is the conjugate base of a weak base, ammonium. So we have, ammonia. We have ammonium ion here. That's going to act as a weak acid. We have a strong base here. The strong base is going to react completely with the weak acid. So it's going to be a stoichiometry problem first. So we're going to use our IF table or ICF table, whichever you want to use, before we do our ICE table. Okay, so we start with our reaction here. So this is going to be the complete reaction. So we have the ammonium ion, which is acting as a weak acid. We have the hydroxide ion. That comes from our strong base, NaOH. Notice that the chloride ion and the sodium ion are nowhere to be found because they are neutral ions. The sodium ion obviously comes from a strong base, and so therefore it's not going to do anything with water. So it's not going to want to go in the reverse direction. Also, the chloride ion, again, that comes from a strong acid, HCl, for example. And so we recognize that that's going to be a neutral ion. It's not going to react with water to reform HCl, right? So we just have these species that are the main players, the players in the reaction. And so this is going to go 100% this way. And so we're going to do stoichiometry first. That's what the ICF or IF table is, right? So for example, we're going to do I. I is for initial. Let me get a different marker here. Okay. And then you could do C for change, and then F for the final. And here, remember, when you're doing stoichiometry, you have to go to moles, right? You got to convert to moles or millimoles. Millimoles is probably easier to use given the fact that it gives you nice numbers. You don't have to deal with decimal places. Like, so for example, we would convert milliliters times the molarity. That's going to give us millimoles. Now, normally you might convert to moles, so you convert this to liters and then multiply liters by the molarity. That would give you 0.050 moles. And so you could use that number, but that's, it's a decimal point. It's not, it's unwieldy in a way. But if you just if you keep this in milliliters and multiply milliliters by the molarity, then you'll get millimoles. And so that would be 50 millimoles. So let me just, oops, oh my gosh. That would be little m, MOL. So let me, again, let me go over the math really quick. So here you would take 100.0 milliliters, multiply that by the, 0.50 molar. You multiply that together, you get 50 milli, oops, I keep saying milli, whatever that is, millimoles. Okay, so that's where I get millimoles. 50 seems to be an easier number to work with than 0.050 moles, right? So that's why we prefer millimoles, because they're just kind of nice numbers to work with. then you could do the same thing with the hydroxide ion. So you have 15 milliliters times 2 molar. So if you do that calculation over here, so we'll do, what is it? Yeah, so 15.0 milliliters times 2.00 molar. That's going to give us 30 milliliters. So technically, if we're going to be technical, since we have 4 decimal places here, we have, or I'm sorry, 4 sig figs. Here we have 2 sig figs. So then you end up with 2 sig figs there. Here we have 3 sig figs. Here we have 3 sig figs. So we should have 3 sig figs here. So 30.30 would be the correct number, right? But probably doesn't matter that much. But you know, let's get things right. Okay, so we have 30.0 millimoles here. This is going to react to completion, right? So we have less millimoles than for the hydroxide ion versus the ammonium ion. This is a 1-to-1 ratio. So all of this is going to react completely with this. This is going to be our excess reagent. This is our limiting reagent, right? So the change here is we're going to lose all 30 millimoles. And then we're going to react 30 here as well. So we're going to lose 30 millimoles here, right? Here we start, we don't care about water, right? Water is not important for us. And then we got 0 amount here of the ammonia. So if we lose 30 millimoles here and it's a 1-to-1 ratio, then that means we're going to gain 30 millimoles here. So we're going to gain 30 millimoles here. So obviously this is going to go to 0. So we don't have any hydroxide left. We're going to subtract 30 here. So we're going to end up with 20 millimoles of our acid. And then we're going to end up here with 30 millimoles of our conjugate base, which is the ammonia. And so you can see right here that we have some of our weak acid, some of our conjugate base mixed together. Now we have a buffer, and we created this buffer by reaction, by partial reaction, right? We didn't mix the conjugate acid and the conjugate base. I'm sorry, the weak acid and the conjugate base together. We didn't make it that way. We made it by partial reaction of the weak acid in this case. So now that we have this done, we now can do the equilibrium problem. We can do an ice table problem. And again, we can write our equilibrium equation in 2 different ways. We can write it from the perspective of the weak base reacting with water, right? So we can write it from this perspective reacting with water, or we can write it with the perspective of the weak acid reacting with water. So I will show both of those. Stay tuned. I will be right back. Oops, I forgot one thing. I wanted to point this out. So here we have the equilibrium constant for this reaction. And the one thing I want to point out here that I forgot to point out is I said this is 100%, this reacts to 100%, it reacts to completion. Well, how do we know that? We can look at the equilibrium constant. So for this reaction here, it's important to recognize how these are related to other reactions. So if you notice here, if you go this way, you get the ammonium ion reacting with hydroxide to give you water and ammonium. Well, if you pay attention, you'll notice that if you go this way and we look at these as reactants, you have ammonia reacting with water to give you hydroxide and the conjugate acid, the ammonium. That is the reaction for the dissociation or I should say the reaction of of a weak base, right? So that's Kb, right? So if you want to remember the definition, or you should remember the definition of Ka and Kb, right? So your Ka values come from the reaction of a weak acid with water to produce whatever the products are. Usually it's water and something else, right? So that is by definition what Ka is. And Kb is, as you can imagine, is the equilibrium constant with respect to a base, weak base, reacting with water to give you hydroxide ion and the conjugate acid, right? So those reactions define what Ka and Kb are, right? So if you can recognize that, look, I have a weak base here reacting with water to produce hydroxide ion and the conjugate acid, that's Kb, right? That's related, that's the reaction for Kb, the equilibrium constant for the reaction of a weak base with water. And so if we want to find the K value of this reaction here, these forward and backwards reactions are related to each other by the reciprocal of each other. So this K value, the K value or the equilibrium constant for this reaction is the inverse or reciprocal of the K value going in this direction. So here we have the K value for this reaction is 1 over Kb, because this reaction's K value is Kb by definition. So we can easily look up the Kb value of ammonium. We can't look up the Kb value or the Ka value for the conjugate acid. It's not in the tables, right? So you start with this. And so you got 1 over Kb, you look at that up, it's 1.8 times 10 to the negative 5. You take the inverse of that, you get this value. So this is the K value for this reaction, right? And why is that important? Because notice that we have a very large number here. This is a positive exponent to the power of 4. So this is a huge number, much, much, much greater than 1, which tells us that this reaction is going to go to completion. The products are much more favored in this reaction, so that's how we know that this is going to go to completion. So I just wanted to share that before going on. Now next, let's go to the equilibrium problems. Okay, we're back. So now we're going to do some equilibrium. So this is the second step to this problem. So we need to find the pH. So now that we've done the complete reaction and we know how much of the conjugate base and acid, now we can do an ice table and figure out what the equilibrium is at this point. So we've done the complete reaction, but now we need to get the reaction to equilibrium. It's not at equilibrium right now. We just did the complete reaction in one direction, but now we have to get it to equilibrium and see what the pH is at equilibrium. Now, first I want to point out, we're going to start with the conjugate acid reacting in water, right? So that's one way you could do it, or you could do the reaction of the base with water, right? So either way should work. I'm going to show you both ways to show you that either way works. Now, before I get into the ice table, I want to show you that in this case, we would need to calculate the Ka, because again, the conjugate acid of the base ammonia is not going to exist in tables. You have to calculate it. But the Kb of ammonia will indeed be in a table or given to you in the problem. So you just look it up or use whatever they give you. And then using this equation, which you all should know, right? So Kw, the equilibrium constant of of water, right? The autoionization of water is equal to the Ka times Kb. Right? So then if you solve this equation for Ka, that's going to be equal to Kw over Kb. You should know that Kw is 1 times 10 to the negative 14. And then you look up Kb, or it's given to you, and you divide the two, and you get, this is your Ka value for ammonium. Now, what's important about this is that this is a negative 10, so this is a very, very, very small number. I'll come back to this in just a moment. But this is going to be important for indicating whether we can use the x is small approximation or assumption for solving this problem. So let's get started. Now, it's really important that you remember when you go from the IF or ICF table where you're doing the stoichiometry and the complete reaction in millimoles, you need to remember that you need to switch back to concentration when you are doing your ICE table, because the K value is related to concentrations, not to moles or millimoles, right? So you have to also remember that you mix things together, and so now you have a new volume, right? So the volume here is going to be the 100 milliliters of the one solution mixed with 15 milliliters of the other solution. So to get back to molarity, you're now going to have to use 115 milliliters of the total solution that you had mixed together, right? So be careful of that. A lot of students will forget that. So when you calculate the molarity of the ammonium ion, it's going to be the millimoles we had before. So let me just remind myself what was the millimoles. So that was going to be 20 millimoles. So we had 20 millimoles, 20. So we had 20 millimoles. So we're going to take 20 millimoles, divide that by 115 milliliters. The milli in both cancel out. We have moles over liters. That's going to give us, what's the new concentration? That would be, let me calculate it really quick, 0.173. So that's going to equal 0.173 molar. Again, technically this should be 2 sig figs, but I'm keeping an extra sig fig to avoid rounding mistakes. Always keep an extra digit to avoid rounding errors. And so I'm going to have 0.173 there for molar. We don't care about water because it's a liquid. It doesn't end up in the K value or the equilibrium constant. Here, this starts off as 0 initially, and then we had here for the ammonia, we had there 30 millimoles, or 30.0 millimoles. And again, that's going to be divided by 115 milliliters. The milli cancels out. We have moles over liters. And that ends up becoming 0.260. 0.260 molar. And so we're going to put that here. 0.260 molar. Okay, so now we have our initial conditions set up. Now we can do the equilibrium setup or equilibrium change. So the change here is going to go in this direction. Why? Because we have 0 as a product over here. So it's going to be going into the direction to make more product. Because at equilibrium, you're not going to have 0 of anything, right? So if you have 0 to start with on either side, you know it's going to go that direction to fill in the void, right? So we know it's going to go in this direction. So we're going to subtract an X amount from here. So some of this has to be used up. And it's a 1-to-1-to-1-to-1 ratio. So that means that if we lose an X amount here, we're going to gain an X amount here. And we're going to gain an X amount here. So then the equilibrium concentrations in terms of X is going to be 0.173 minus x. This is going to be just x. 0 plus x is x. And then this is going to be 0.260 plus x. So now we have our equilibrium concentrations in terms of x. So now we can set up our expression for the K value. So this is going to be Ka, right? So this reacting with water. So the Ka for this, the expression is going to be the concentration of products over the concentration of reactants. So here, it's going to be the concentration of H3O plus times the concentration of the ammonia, right? So here, we're now going to divide by the concentration of the reactant, the ammonium, NH4 plus. Excellent. So now all we have to do is substitute or put in these expressions. So this is going to be x, so this is going to be equal to x multiplied by NH3, the concentration of NH3, which is this expression here. So it's going to be 0.260 plus x divided by, and then the expression for the concentration of ammonium, which is this right here. So we're just going to put that in, 0.173 minus x. And so now we have our Ka expression in terms of x. So here is where we can do the x is small approximation, and that is justified by the fact if you compare the initial concentrations that we have with the Ka value of this reaction, you'll notice that the initial concentrations are much, much larger than the Ka value, or another way is that the Ka value is much, much smaller. Very, very small compared to the starting concentration. So that means that although it's going to go in this direction, this means that the products are not very favored by this reaction. So the reactants are much, 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 much more favored. So a tiny, tiny, tiny bit is actually going to go this direction, which means that the concentrations, the initial concentrations shouldn't change all that much, right? So x is going to be so small that, well, not that x, we don't want to ignore that x, but the x is going to be so small that if you subtract or add to these numbers, they're really not going to change. So we can ignore it. It's negligible, right? So anytime the factor of 10 is 3 or greater difference between the factor here of your initial concentrations, then it's safe to say that the 5% rule will work and you don't really have to do it unless your teacher or professor says you should do it and show it. Now, if it was like a factor of 2 or a factor of 100, I should say, then you probably, you probably should do the 5% rule and calculate the 5% or the percent error or the percent dissociation and see if it's within 5% or greater. So here we can ignore x. Excuse me. So we can ignore x here. And so now all we have to do is solve this for x. So remember the Ka value we calculated is this here. So that's going to be equal to 5.56 times 10 to the negative 10. So here we have x times 0.260 over 0.173, and that's equal to 5.56 times 10 to the negative 10. So we just solve for x. So we multiply by 0.173 on this side and this side, 0.173. So that cancels out. Now we divide by 0.260. On this side, we're going to divide by 0.260 on that side. So this cancels out. Now we have x equal to this. And so when we calculate this out, we get 3.69. Oops. 3.69 times 10 to the negative 10, I believe. 10 molar. And so this is equal to x. And you can see that, look at the change that we have for x. So that if we subtract this from this number, it will hardly change, especially with sig figs, right? If you subtract x, this is going to have 3 decimal places. The decimal places for this number are going to be much, much greater. So when you subtract and then round your answer to the proper number of sig figs, it's going to end up being the exact same number. So no effect whatsoever. So then this is very small. This justifies our x is too small. And then if we actually did the 5% rule, we will find that the percent is much, much, much less than 5%. So now we can use this. Why? Because x is the hydronium concentration, which is what pH is based on. So now we can calculate the pH of the substance. So we can erase all of this to give ourselves some room. Right? So now we say, okay, well, the pH is equal to the negative log of the hydronium ion concentration, or H plus concentration, right? That's what pH means. So H here represents the H plus concentration, just in the same way that your pKa is the negative log of your Ka value. So anytime you see P something, that indicates you're taking the negative log of it. So now here, I take negative log of the H3O plus, which is this number here. So 3.69 times 10 to the negative 10 molar. And then here, I take the negative log, and I get 9.432. So 9.432 for the pH. Okay, and there you have it. And so here, I just want to point out sig figs again, what the rule is. Now here I kept an extra digit here. So technically this is 2 sig figs in my answer. And so when you take the log of a measurement, the way that translates into sig figs is the number of sig figs here translates into the number of decimal places here. So here I have 2 sig figs. So technically I should have 2 decimal places. So this number here is a extra digit that was kept because of the 9, right? So here, if I did 3 sig figs here, then I end up with 3 decimal places. This here is just an extra digit for rounding mistakes. I don't want to round this number before taking the negative log because, again, you'll get rounding error in your answer. So I keep the 9, and so here I have 3 sig figs, so I end up with 3 decimal places. But again, if I was to record this, then I would just record the 9.43 as my official final pH measurement. Okay, and so that is how you find the pH under the conditions of conjugate acid in water. Now let's look at how you would do that if you did the weak base in water. Okay, so now we're going to do the same exact thing, but now we're going to start with the conjugate base. We're going to do it in the from the perspective of the conjugate base in water. And so all we did here is we are now taking the base here, the conjugate base, NH3, which is ammonia. That's going to react with water now to form the hydroxide ion and NH4 plus. So in this case, instead of finding the H plus concentration, we're going to end up finding what the OH minus or hydroxide concentration is, and then we're going to have to do that from the pH or POH. So here, because we're doing the base reaction problem with the weak base reacting with water, we can go ahead and use the Kb. We don't need to calculate it because that's going to actually be in a table. So we can use that. So we could set up our ice table just like before. And so now, starting from what we had before, we had 20. Again, the concentrations are going to be the same. So we're going to here have, let's see here. So our NH2, hold on a second. Sorry, meant NH4 plus concentration here. So the NH4 plus the NH4 plus concentration was 0.173. So again, that's going to be on this side, 0.173 molar on this side. And then on this side, it was 0.260 molar. Let me double check that. Yes, 0.60 molar. Okay, so now, again, we don't care about water. And this is at 0. So again, because we have 0 product on this side, it's going to shift towards the product because we got to fill in that vacuum. So you're never going to have 0 of anything at equilibrium. And so we know we're going to lose an X amount here. We're going to gain an X amount here because it's a 1-to-1-to-1-to-1 stoichiometric ratio. And then we're going to gain an X amount here. And then when we figure this out, their equilibrium is going to be 0.260 minus X. This is just going to be X that we gained. And this is going to be 0.173 plus X. Now we can put this into our equilibrium expression. So let's write that out. So in this case, Kb is going to be equal to concentration of products over the concentration of the reactant, again, ignoring water. So then we're going to have the concentration of OH minus multiplied by the concentration of NH4 plus over the concentration of NH3. And so all we have to do now is plug in these expressions here. So this is going to be equal to X times, and then we're going to have 0.173 plus X over 0.260 minus X. And this is going to be equal to the Kb value, so that's going to be equal to 1.8 times 10 to the negative 5. Now, I want to, again, let's look at the Kb value, our K value with respect to the initial concentrations that were given. And you'll see that both of these are about, times 10 to the negative 1. Right, so here we have times 10 to the negative 1. If I was to write this into scientific notation, we'd have 2.60 times 10 to the negative 1. Here we would have 1.73 times 10 to the negative 1. So here, if we look at the exponents of the power of the base 10, so the negative 1 compared to the negative 5, that's a four, I shouldn't say fourfold, that's a factor of 10,000 difference. Right? Or so 10 to the 4 is 10,000. So So the difference between the K value here and the initial concentrations is a factor of 10,000, which is very large difference. And so in that case, you can say, well, the 5% rule is most likely is going to be valid here. Now, if the factor difference between these was like 100, like 10 to the 2, then in that case, I would just do the 5% rule calculation, see if it's where it is. It probably won't be valid in that case, but if it's 1,000, a factor of 1,000 above, right, then you could pretty much guarantee that it's going to be valid. The 5% rule is going to be valid. So here we can say, okay, X is going to be negligible in this case. And again, the thought we have is that this is so small that the reactants are much highly favored compared to products. So it is going to go in this direction, but a tiny, tiny, tiny bit. So the amount of hydroxide ion you're going to form is going to be very tiny. So we assume it's negligible. And so now that we have this, we can have, if we rewrite it, we have X times 0.173 over 0.260. That's going to be equal to 1.8 times 10 to the negative 5. And then we want to solve it to get X by itself. So we're going to multiply both sides by 0.620. And we're going to multiply this by 260. So this cancels out. Then we're going to divide by 0.173. Over here, we'll divide by 0.173. So then this cancels out. We have X by itself is equal to this. And then if we calculate that, we get, what do we get? 2.70 times 10 to the negative 5 molar. And once again, you can see that this is much, much smaller than the initial concentrations. And so if you were to subtract this or add this to these numbers here, you would end up getting the same numbers back, especially when you round them to the correct number of decimal places or sig figs. So again, that indicates or proves that we were right to assume it's negligible and ignore it from our calculations. So now we can take this. Now you have to be careful. This is not hydronium or H plus concentration. This is hydroxide concentration. So we're going to have to use this to calculate the pOH. Or you could take this and calculate the H plus concentration using that the concentration is equal to is multiplied together equal to 1 times 10 to the negative 14. Either way is fine. I'm gonna use the pOH calculation, so we can go ahead and get rid of this since we don't need it anymore. So here, pOH is equal to the negative log of the OH minus concentration, which is what we have here. So then that means that's going to be equal to the negative log of 2.70 times 10 to the negative 5. And then that gives us 4.567. 4.567 for our pOH. And again, we want to find pH, so we know, or you should know, that pH plus pOH is equal to 14. So then we plug that in. So pH plus 4.567 is equal to 14. You don't need this anymore. And then that means that the pH is equal to, what did I calculate it? 9.432. 9.432. And again, throughout all of this, I kept an extra digit. So this is an extra digit. So remember the rule, when you take the log of something, then the number of sig figs becomes the number of the decimal places in your resulting pH or POH. And again, since this is an extra digit that I kept to avoid rounding mistakes, this also is an extra digit to avoid rounding mistakes. So I subtract that from here, and so I ended up getting that. So if this number is different from the number I got before, but that's just an extra digit. So if I keep that, we get the exact same pH value. Okay. Now, one last thing before I finish up. Let's try this with the Henderson-Hasselbalch equation. One thing you should know regarding the Henderson-Hasselbalch equation is that the Henderson-Hasselbalch equation is valid to use if your assumption that x is small approximation is valid. So if your 5% rule is valid here, then so is the Henderson-Hasselbalch equation, and we know that it's valid here because, as I said, the Kb value is much smaller than your initial concentrations by a factor of 10,000. So therefore, the Henderson-Hasselbalch equation should work. So let me finish up quickly with the Henderson-Hasselbalch equation and see if we get the same value. So stay tuned. Okay, last but not least, let's look at the Henderson-Hasselbalch equation. So we're going to do an alternate calculation. We're going to do the acid because the Henderson-Hasselbalch equation is based on an acid reacting with water to get the conjugate base, right? So we could do it the other way around, but we would use a different version or derivative of the Henderson-Hasselbalch equation, which I won't get to in this video. So here is the reaction of the ammonium with water to give me a hydronium ion and the conjugate base ammonia. And here's the calculation of the Ka value for the reaction with regard to the weak base or the weak acid here with water. We got that before, so it's 5.6 times 10 to the negative 10. And here's the table that I had before, but slightly different. Here you'll see that I have 20 millimoles divided by 115 milliliters. And then that came to, oops. Sorry about that. And so here, when we did that calculation, that was something like 0.173 molar, right? Or so 173 molar. And this, when we calculated, was 0.260 molar. I'm keeping it in this form to show you something that occurs in the Henderson-Hasselbalch equation. That's important to remember. And that is, if you remember, the Henderson-Hasselbalch equation is the pH is equal to the pKa plus the log of the base over the acid. So if you remember this equation, you can then plug in the stuff that you know here and solve for the pH. Now, this, again, like I said, this only works if the value of the x is so small that it's negligible. And so in that case, if you find that the value for K is so much smaller compared to your value of your molarity or the concentration you start with, then you can assume it's negligible. And then you'll see what happens if we get rid of this, right? So if x is small, you'll see that the starting concentration and the equilibrium concentration is exactly the same. So we can now use that. We can use the equilibrium, the initial concentrations and plug those into here. Now, the thing I want to point out is notice that when I plug these in for base and acid, the concentration of base over the concentration of the acid, right? So let's start to fill this in. pH is equal to the pKa. Remember, P means negative log of, right? So here I'm going to take the negative log of the Ka value, which is that value there. So 5.6 times 10 to the negative 10. And then this is going to be plus the log of the base, the concentration of the base, which is the ammonium. So it's going to be 30 millimoles. So we're going to put 30 millimoles over 115 milliliters over, and then the concentration of the acid, which is this right here. So it's going to be 20 millimoles over 115 milliliters. And this is what I want to bring to your attention, is that notice that the volume is the same here, right, when we do concentrations. Now, technically, you're supposed to do concentrations here, but if you notice that because both of these species are in the same volume, this volume units are always going to be the same. So when you divide these, they end up canceling out. And you could just put your millimoles in there, or moles, right? But again, millimoles is more convenient to you. So if you've already calculated the millimoles, why spend the time to calculate molarity again? So this kind of saves you some calculations. You don't have to actually calculate the molarity again if you've already got millimoles after you've done the first part where we did the completion part, the stoichiometry part where you did your IF table or your ICF table first. Then you could just plug in the millimoles here, base over acid, and then do the calculation. But again, this only works if the 5% rule is valid, if the X is small approximation is valid, which in this case it is. And so we just take the 30 divided by the 20, find the log of that, add it to the, that should be negative, the negative log of this, and then when you do that, you get 9.431. So we get 9.431. And again, this is just an extra digit that's kept. So the actual value is this, which is exactly what we got before. So the Henderson-Hausbach equation works under these conditions. So this is a quicker way to do it if you're paying attention. So I just lost my marker. Thanks for joining me. I hope you enjoyed this video. If you liked my video, if you like all my videos, then please hit the like button. Also, make sure you subscribe to my channel. Hit that notification button up there so that way you can be notified by all the videos I put out. And finally, put a comment down below. Let me know what you think. Maybe you laughed at the fact that I just dropped my marker. Or if you have any questions that pop up or you need help with anything, please let me know. Thanks for joining me and have a great day.